So this lesson is sinusoidal functions, lesson 1 and 2, actually, is what it's called. Really what I want to do, this first little section that you can see here is just a pattern. Now, some of you, as you were walking in, were looking at this pattern. Some of you already figured it out. If it goes 10, 20, 30, 40, 50, 40, 30, 20, 10, 20, 30, 40, 50, 40, 30, and you continue the pattern, okay? You know that what it's doing is it then goes to 20, then it goes to 10, and then it starts to return the other way. So it goes back up to 20, then to 30, then to 40, then to 50, and then it's hit its maximum. It stops and it goes back down 40, 20, 40, 30, 20, 10, and then it's at the minimum, and then it keeps going. It's this type of pattern that this unit is about. This is a periodic pattern or a repetitive pattern, okay? So that it just keeps doing the same motion or the same situation over and over and over and over and over again. If you start looking at phases of the moon is a repetitive pattern because it goes new moon, half moon, full moon, half moon, new moon, half moon, full moon, half moon, and it just keeps doing it over and over and over and over and over again. And that's what this unit is about, these repetitive patterns. Now, up until now, the first couple units, the last little while, we've talked about exponential functions, logarithmic functions. You've talked about linear, quadratic, and cubic functions. Well, this unit is going to talk about a different type of function. Now, before I talk about that function, this is your notes. Angles is the heading. What I need you to stop and think about is angles, because I need to introduce a new type of angular measure. Now, degrees. Where did degrees come from? Have you ever thought, asked, wondered, figured, why? Why 360 degrees in a full circle? Why? Why 180 degrees in a triangle? Why? It's not like God came down and said, "Thou shalt say that there should be 360 sections or degrees of a circle." That never happened. Honest to goodness, the 360 degrees, while there's logic behind some of those guesses, the 360 degrees is entirely random. You know why we do 360 degrees? Because some guy in history said, "I'm going to take a circle and put it as 360 sections." And everybody else said, "Okay, sounds good." And they left it at that. That's what happened. Okay? Somewhere along the line, somebody said, "This seems to make sense to me." And they went and did it. And everybody said, "Sounds good." And they've just kept doing it. There are lots of different ways to measure angles. Degrees is the one you learn about in junior high or elementary school, and we just kind of continue on. You are at the level now where we're going to look at a different type of angular measure, because degrees isn't natural. It's not like 360 naturally shows up and just boom, as you stand out and look and see it. Okay? 360 is man-made. Somebody came along and said it. There's gradients. Gradients is one. If you had an old calculator, you may have noticed at the top it says deg, rad, grad. Okay? Often those are at the top of a calculator, old-fashioned calculators. Gradients, somebody said, let's say a full circle is 400. It's 400 gradients. So a perfect corner, instead of being 90 degrees, it's a quarter of the circle, so it's 100 gradients. There are lots of ways to do it. If you're doing surveying, there's degrees, minutes, and seconds. There are lots of ways to measure various angles and things like that. But why have we done this? Because, B/C, because someone said so. Okay? Somebody came along and said, let's make it 360. And everybody said, okay. And that was the end of it. And since then, it's kind of stuck. There are methods of measuring angles that are more natural. Okay? It says here, degrees are human-made. There are other ways to measure angles. One of the ways we discuss in high school trig is called radians. And that's what I want to talk about with you here. A radian is the central angle of a circle when the arc length is equal to the radius of the circle. Now I'm going to draw that, okay, and I'll explain that because it sounds really wordy. It sounds really confusing. But a radian is more natural. So if you look at this, and I'm going to kind of move this off. Please stop copying for just a sec. Looking over here, what do I mean by radians? Well, if I look at a circle, oh, there's a beautiful circle. If I look at a circle, okay, and I have the center of a circle in here, And that center of the circle, this circle has some radius. Okay, I'm just going to call it r. And it doesn't matter where I put it. If I put it here, it's r. If I put it there, it's the same thing. Now I know my circle doesn't look perfect. I understand that. But with a circle, those are the same. If the outside edge, this section of the outside edge, is the same as the radius, you kind of got this sector or segment that is kind of, for lack of a better word, equilateral in the sense that each side is the same. There's an angle in here, and this is 1 radian. Okay? That's what that definition is trying to say. If the length of an arc is equal to the radius of the circle, then the central angle is 1 radian. That's defined that way. Now, that seems really weird, but what that means is there's 2 pi radians in every circle. Now 2 pi is 6.28, so I think later in the notes it says 6.28, because it's 2 times about 3.14, so it's about 6.28. Where does that come from? Why am I saying that's more natural? Well, what happens then is this angle of the circle is the circumference of the circle. So if I look at a circle of radius 1, and the circumference is 2 pi r, that's a formula from junior high, the circumference of the circle is 2 times pi, and if the radius is 1, 2 times pi times 1, the circumference would be 2 pi. If the whole circumference is 2 pi, and I'm talking about the angle being equal to the circumference, using the radius of 1, then I get every circle has 2 pi radians. Now why 2 pi? Same reason that it's 2 pi in the formula. Okay? That's what ends up happening. And so these are more natural in the sense that they show up and they form a little bit of a basis. Why don't you learn about them in junior high? Because if I say there's 6.28 and da-da-da-da-da-da-da-da-da in a circle, how are you going to use a protractor? Okay. Well, okay, so half of it would be 3.14, so that would be your 180 degrees. And then you get 1.57-ish, and then you end up with so many decimals, it's confusing for kids. I mean, decimals are hard enough. You didn't learn about them till grade 7. Okay? And so decimals cause people confusion. We start talking about angles in elementary school. They talk about right angles and acute angles and obtuse angles and that sort of thing. Because we need to talk about it early because it forms the basis of geometry, they picked something that made sense that kids could understand. And understanding 90 degrees and 45 degrees made something that the kids could understand. It's permeated language. Okay, when you're running a business and you got a business plan and you're heading towards some destination and you suddenly realize, oh crap, we screwed up. We've got to turn around and do a full 180. Okay, that's 180 degrees. You're going in the opposite direction. Okay, conversational geometry. There's a Dilbert cartoon that talks about it. It's making fun of people that don't understand conversational geometry. You've got pointy-haired boss that says, well, our business plan is going in the complete wrong direction, so we've got to pull a full 360. If you go 360 degrees, you're still heading the same direction. It's not helpful. And so the comic is all making fun of people that don't understand that. Okay, and so that's the general idea. 360 degrees, 180 degrees, 90 degrees form a basis of our society, but they're not natural. Somebody came up with them. So a radian is the central angle in a sector of a circle when the arc length is equal to the radius of the circle. There are approximately 6.28 radians in every circle, or 2 pi. Okay. Now in Math 30-1, you have to investigate that a whole lot more. And they do conversions, and they look at it in terms of exact values, and you talk about pi's over 2 and pi's over 6's, and they have to memorize certain things about different values of pi, different angles. You guys don't. The extent of what I need you to understand is there are lots of ways to measure angles. One of them is degrees. We're quite comfortable with that. Another one is radians. Okay? And radians are based on the circumference of the circle, using the whole circumference equals 2 pi r formula, and so you've got a central angle, 2 pi. Now, your calculator can function in both degrees and radians. It hasn't mattered for the rest of this course up until now, because the only time degrees and radians ever matter is when you're using sine, cos, and tan, the sin, cos, and tan buttons. Okay? If you're using sine or cos or tan, then it matters what mode you're in. When you first learned SOHCAHTOA back in grade 10, or sine, cos, and the ratios, opposite over hypotenuse and all that jazz, that was when all of a sudden in grade 10, whoever taught you math started to say, you need to make sure your calculator's in radian mode or degree mode. And they went and did that. And then when you were filing into the gymnasium for the final exam, and there was a whole math department, and they're standing there and they're resetting your calculator and they're putting that cute little sticker on it that's usually a circle colored dot, okay? The teachers will often say, do you need me to put it back in degree mode? Do you know how to put it back in degree mode? Or they'll just remind you that it's in radian mode, because when you reset your calculator, it defaults to radian. So for Math 10 and Math 20, when you're doing SOHCAHTOA and sine, cos, and tan, and the sine law, the cosine law, in Math 20-1, when you're looking at angles in standard position, since everything's in degrees, you need to put it into degree mode. I haven't mentioned it in this class before. If some of you, in fact, there was one person back in September that came and asked me, do we have to be in degree mode? And I said, no, it doesn't matter. It didn't matter for the rest of the course, because nowhere in the probability or perms and coms or logs or rational expressions, nowhere in there was I using sine, cos, and tan. So that's why it didn't matter. It doesn't matter. But now with this unit I'm using sine, cos, and tan, I need to fix that. So your calculator functions in both degrees and radians. When you're in Math 10 or Math 20, when you're in Math 10 or Math 20, you need to be in degree mode. Okay? For this course, you need to be in radian mode. Okay? Now the nice part is when your calculator's reset at the door of the diploma exam, it will be in radian mode. The teachers should know, but if they don't let them switch it back to degree mode. Neither you nor the 30-1s will need degree mode. You will need radian mode. So you don't want them to swap it. Okay? But if you're not sure, or if you're in a science course where you're doing vectors or something like that, and you need to use degrees, you have to be able to push that back and forth. So you're going to push the mode button. And when you do that in the mode button, and I'm just going to kind of go through and load up my calculator, when you do the mode button, it brings up a list. Now, depending on your model of calculator, it looks a little different. If I push mode, which is right up at the top, mode, it brings up a list like this. Now this, on my screen here, I've got a TI-84 plus C. It's a fancier one. So it can fit lots of different things on there. You don't have, probably, the entire list. But the third or the fourth option down, depending on which calculator you have, is radian or degree. Whichever one is highlighted is the mode that it's in. You want to make sure it's in radian mode for the remainder of this course. Keep in mind, if you're doing physics and you're talking about momentum, or Science 30 and some of the stuff that you do in Science 30 with the physics stuff, you will need to switch back and forth between degree mode and radian mode. So you'll just have to start watching for that. But you just fix that. So in radian mode. So make sure radian is highlighted. Okay? You need to make sure radian is highlighted. The question that came up in the other class was, what if you're in the wrong mode? Being that it's multiple choice, numerical response, the multiple choice questions will the first one at any rate, if you do it in the wrong mode, you won't get the answer that's there. They won't try to trick you. If you do it right but have it in the wrong mode, that answer won't be there. Okay? I can't speak the same for physics. I don't know if that's true. I can't imagine it is. But you've got to put it in degree or radian mode. Now, can I move that up? Are you guys okay with that? Yeah? Periodic or sinusoidal functions. Here's more notes. A periodic function. Okay, that's that first definition. A periodic function repeats the same pattern over and over and over and over and over again. Phases of the moon. New moon, half moon, full moon, half moon, new moon, half moon, full moon, half moon, new moon, half moon, full moon, half moon, so on and so forth. It just keeps repeating. It takes about the same amount of time every time. So continuing with this one here. Periodic function is a function that repeats a pattern. So it goes up, down. Goes up to a maximum, down to a minimum. Sinusoidal is almost the same thing. Sinusoidal has more of a rounded nature to it. Periodic doesn't have to be rounded. It could be pointy. It could look like a mountain range that a kid has drawn. Okay? Sinusoidal looks very smooth. Okay? Now a sinusoidal function, this word here that I'm searching or circling is sinusoidal, just so you know. Okay? Because it's a confusing looking word, sinusoidal. It basically means sine-like. Okay? And you'll understand that in a minute. It's a periodic function that has a particular curve, but it appears slightly rounded. Okay? It's basically caused by motion around in a circular sort of pattern. So, many situations can be modeled by a sinusoidal function. Sunrise time. Sunrise and sunset time, they repeat. Okay, if you've ever watched the news, if you turn on CFRN News and you watch Josh Clausen, and he's sitting there and he's doing his weather report. It's almost always the weather guy. And he's doing his weather report, and in his weather report he says, the sun will rise tomorrow at 6:32 and set tomorrow evening at 7:15. He doesn't have, it's not like he has a crystal ball. It's not like he's guessing. It's because it is a sinusoidal function. Based on the year, based on the day of the year, they can calculate it. There are functions that will tell them to almost the minute where it'll rise and where it'll fall for each of the major cities. Okay? They've gone and looked at that. Further, closer you are to the equator, the closer they are together, the flatter it is. But nonetheless, you've got that sort of idea. It's a sinusoidal function. It truly is. The height that you are if you're riding a Ferris wheel or if you're looking at a bucket of a water wheel, it goes up to a top, down to a bottom, up to a top, down to a bottom, up to a top, down to the bottom, up to the top, down to the bottom. I mean, I couldn't imagine anything more boring than being like a car, a little seat on a Ferris wheel. I mean, obviously, it's not a real thing. But all you do is go up, down, up, down, up, down, up, down. That's all that happens. Alternating current, the electricity that's in your wall. Okay, alternating current is a sinusoidal function. It oscillates. It goes to a maximum one way and a maximum the other way. A maximum one way, maximum the other way. You could research that. That alternating current versus direct current is actually really, really interesting. Ask Ing, if you have Ing, about Tesla. Nikola Tesla, or Nikolai Tesla, whatever his first name is. He was a big proponent of the alternating current. Pendulums, if you watch a pendulum on a grandfather clock, goes to the left, to the right, to the left, to the right, to the left, to the right. It has a maximum and then a minimum, and then a maximum and a minimum. Phases of the moon. New moon, half moon, full moon, half moon, new moon, half moon, full moon, half moon. I just like saying that. But ladies and gentlemen, if you see the maximum amount of the moon, the whole face, you see the minimum amount of the moon, nothing. And then it keeps going. There's all sorts of examples that are sinusoidal in nature. Okay? If you've taken Physics 20, you talk about waves. Now, each of those functions, every sinusoidal function, has the following characteristics. It has a median, it has an amplitude, and it has a period. I'm going to let you copy this, okay, and then we'll talk about it. So in these, this is the characteristics of a sinusoidal function. Every sinusoidal function has a median value. Now, median is essentially the middle value. It goes up to a maximum of whatever it's measuring. It goes down to a minimum of whatever it's measuring. The median is whatever's directly in the middle, halfway between the top and the bottom, halfway between the max and the min. Okay. Sometimes we have a midline as well. Okay, I'm going to illustrate that with an example. It's essentially the median. It's just written a different way, so don't worry about that. But I want you to know middle or median, midline or median are the same thing. The amplitude. The amplitude is talking about how far it deviates from the middle, how far it goes up to the top, how far it goes down to the bottom. Now, if you've done your middle right, it goes exactly the same from the middle to the top as it does from the middle to the bottom. That's the definition of middle. It's right smack dab halfway between. Goes the same distance up as the same distance bottom. We call that, in terms of a sinusoidal function, we call them amplitudes. Okay? The period. Period is, by definition, the length of time it takes for this function to repeat. How long does it take to repeat? In the terms of, like, if I'm talking about sunrise and sunset time, it's 365 and a quarter days. That leap year adjusts it and fixes it. That's the reason, that's part of the reason why leap years are there, because it's 365 and a quarter days. So they add the leap year in every once in a while to cause the adjustment. In the case of phases of the moon, it's about 28 days. Because in 28 days, it goes from new moon, half moon, new moon again, okay? It comes back. It takes that long to repeat, okay? In the case of alternating current in your plug-in, in North America, it's 1/60th of a second is the period. It turns back and forth 60 times in 1 second, okay? That's why my dad said, oh, you know, if you go to the plug-in, you get electrocuted 60 times in 1 second. And he said that scared the heck out of me as a kid, okay? But nonetheless, I remember him saying that, like, he'd just keep getting electrocuted. And then he would say things like, do you see the light? Because we had incandescent light bulbs, like the old-fashioned light bulbs. And he's like, that keeps turning on and off 60 times in 1 second. And it kind of does, but it never stops glowing, because even when it turns off, it's not enough time for it to cool down. But nonetheless, that's the idea. Every sinusoidal or every periodic thing has a period, the length of time it takes to repeat. Now, once you're comfortable with those terms, the median, the amplitude, and the period, we also have talked about the maximum, the minimum, that sort of thing. And so what I'm going to do is I'm going to do an example. So that's this purpose here. Given the graph below, identify the amplitude, the median, the max, the min, and the length of the period. So I'm going to just draw a graph, okay, kind of at random. I'm going to give you some points to help us work on this. So I'm drawing a graph here. That's my y-axis. There's my x-axis. Okay, and I'm drawing a sinusoidal sort of curve. Okay, so I've got that. And it's the same at both ends, so I'm putting arrows on it. And I'm just going to give you points. This is going to be 8, 7, so on and so forth. So there's this graph. I'll give you a moment to sketch it down. I made it up as I was going. Okay, so it makes it a little bit easier for me to write it. So when I look at this, not trying to rush you too much, I have to find the amplitude, the median, max, min, and the period. There are 5 things I have to do. Just because they're listed in that order, you don't have to do them in that order. When I do it, here's the easiest one I find first, the maximum and then the minimum, or vice versa. I find the max or the min first. I find those the easiest. The max or the min is referring to the largest y-coordinate or the smallest y-coordinate. The largest y is 7. The smallest y is -3. It's coming from these. And if it's a nice sinusoidal function, it's always going to be the same. Okay, you're going to ask the question, what if it's 7 on this point and 8 on that point and 9 on the next one and then 6? Then it's not sinusoidal. So all bets are off. Okay? So you're always going to have the same one. So the max and the min. You guys are okay with that? From there, then, the next thing I do is I look for the median. Okay? The median is exactly halfway between 7 and -3. Now, you can do that in a variety of ways. Probably the easiest is add them together. 7 plus -3 divided by 2. Add them together. You're just finding the average of them. Add them together. 7 plus -3 is 4. 4 divided by 2 is 2, so the median value is 2, which is exactly halfway between 7 and negative 3. Okay, 5 from 7, 5 from negative 3. You could look at it that way too. However you do it, it's fine, as long as you see it. Okay. So once that's done, I've got the median value, I've got the max, I've got the min. The next one I usually look at is the amplitude. Now the amplitude is the distance from the median to the top or from the median to the bottom. And if you've done the median right, it's always going to be the same. Always, always, always. Okay, that's the definition of middle. So if my median is this dotted line here, which is at 2, okay, then I'm 5 from the top, or I'm 5 from the bottom. Either way, the amplitude is 5. And the amplitude's always going to be positive. Okay, it's how far you are away. So 5 up or 5 down, whatever, you're deviating 5 from the middle. So you're deviating 5 from the median, so the amplitude is 5. Are you okay with that? This is the one that tends to cause some confusion, so questions. How do I get 5? If I'm going from 2 to 7, I just subtracted 7 minus 2. Okay, does that make sense? Ditto with this one, 2 minus negative 3 is going to be 5. Either way, it's the same difference. Okay? Oh, I could. I just didn't bother because I didn't want to make it too cluttered. It doesn't matter which one I do. Okay? Now, last but not least, the harder one is the period. Now, for the period, okay, what I have to do is I have to pick 2 points that are exactly the same situation, that are doing the exact same thing. So one of the things I can look at is this one, where I'm drawing the big dot, the 2, 7, and this one, drawing the big dot at 8, 7. Those are 2 points that are exactly doing the same thing. They're both at the top. How far apart are they? Well, to go from 8 to 2 or 2 to 8, you have to go 6. So the period is 6. Okay? If it's a sinusoidal function, if it's a true sinusoidal function, it doesn't matter where you go. If I look at these two, okay, I'm going to put the x on the negative 1, 3. You probably can't even see it. And the x on the 5, negative 3. Okay? How far apart are they? Well, it goes from negative 1 to 5, so they're 6 apart. What if it's different? Then it's not sinusoidal. It will always be the same. Now, the biggest confusion happens if you take a point in the middle. If I look, for example, at this one here, okay, I don't know what it is, but if I looked at that one there, to compare it, to find the period, I have to find the next spot that the function is at the same height, going in the same direction. So in this spot here where I've got that dot that I just drew, this dot here, okay, put a little arrow so you can see where I'm pointing, that spot is at that point going up, because as I go through it, I'm traveling up. The next time it's at that point going up is here. Okay, this spot here where I'm drawing the little arrow to draw attention to it. That's the next time. And if I knew those points, and I don't, but if I knew those points, how far apart would they be? The period, 6. Whatever they are, I don't know what they are, but whatever they are, they're going to be 6 apart. Does that make sense? A lot of people will look at a spot, and I'm just going to draw a little line here, where I've got that little horizontal line that I'm drawing. A lot of people look there and say, well, it's at the same height. It's going in the wrong direction, so it's not a period. Okay? So you don't look at that one. You have to, oh shoot. You have to look at the same direction, same height going the same direction. Okay? So on and so forth. I'm going to give you guys another one of these to do to see what happens. Okay, the max is 7, the min is negative 3, the median is 2, the amplitude is 5, the period is 6. Do they have to be whole numbers? No. They can be decimals. Okay? I'm not going to give you decimals in this next question, but I want you to know that they could be decimals. So if I look up at example number 2, I'm just going to draw another grid, okay? And I want you to find the same things, the median, the amplitude, the min, the max, and the period. So there's my grid, okay? Drawing my beautiful sinusoidal function. Actually, I am going to give you a decimal for this one. So for this guy here, amplitude, min, max, median, and period. Please see if you can find it. Work with your neighbor. Okay. All right. In this function here, the maximum is the largest y value. The largest y value is up at the top. It's 12, okay, where that arrow is. The minimum y value is at the bottom, so it's going to be -2. Now, to find the median, you have to find exactly halfway between 12 and -2. Halfway between them, you just average them. Add them together, divide by the number of how many things you had, which is 2. If you add them together, you'll get 14, or sorry, you'll get 10 divided by 2 is 5. The median is at 5. You can also look at it as they're 14 apart, so it's going to be 7 from the top, 7 from the bottom. 7 below 12 is 5. 7 above -2 is 5. The amplitude, though, is 7. It's half the distance from the min to the max. So 12 and -2 are 14 apart. Half of that is 7. The amplitude, once I had the median, okay, and the median is at 5. That's not drawn very well, but you get the idea. If the median's at 5, the amplitude, how much further is that above, or how much further is that below? And 12 is 7 above 5. -2 is 7 below 5. That's one way to do it. Another way to do it would be to look at the difference between the max and the mins. So it's half the difference. From 12 to -2, they're 14 apart. Half of that is 7. That's going to be the amplitude. Okay? The period for this, you have to pick some point, and you have to find out how far it is across to the next version of the point. I'm going to take that max there at -14.5 and that max there at 0.5. How far apart are they? I figure that out. They are 15 apart. Whoops. They are 15 apart. So as such, my period is 15. Make sense? Now going through with that, once you've got this idea, then trying to tie it to the equation. Here's some more notes. Okay? Sinusoidal functions have this form. Okay? In every one of these functions, we've had a form. In sinusoidal, it's y equals a times the sine of bx plus c, close the bracket, plus d. Okay? In 30-1, we talk about a different form. I have rewritten it underneath there so it all ends up on the same form. It's just the resolution of my tablet. But nonetheless, here are some notes, and I'm going to refer to them in a minute. I know there's only 12 minutes left in class. I know I've talked for quite a while. But this is kind of where we're ending up. I'm going to have one example after this. Please copy these notes, and that's where we go. Looking at this, the amplitude will be whatever the A value is. The median will be whatever the D value is. Also, too, that relates to the midline, but I'll show you what I mean in a moment. The period is 2 pi divided by B. That's the only thing that's given to you. The maximum is the D value plus the A value. The minimum is the d value minus the a value. The y-intercept, just like in all of the functions we've done, let x equal 0, just plug it in. Replace x with 0, figure out what it is. Same thing happens with sinusoidal functions. X-intercepts are a little bit more complicated because, in all honesty, if there's any x-intercepts, there's an infinite number of them. If there's any x-intercepts, there is an infinite number of them. And so since we don't talk about like the general solutions, that's what we call it, where we're looking at the infinite solution, okay, we're going to define a range, a lower boundary and an upper boundary, and you look for the x-intercepts between there and there. That's all we ever do. Your calculator will do it for you. You sketch y2 equals 0, and you just find the intersection point for all the x-intercepts, which is the same way we've done all the other ones anyway. Okay? But it will give you a boundary. Now, using this theory, using that theory, and I don't know if you're all done, determine the amplitude, the median, the midline, the period, the max, the min, the y-intercept, and the x-intercepts from -10 to 10 for the equation below. This is my last example for the day. So the equation I'm going to give you is y equals 5 times the sine of 1/2 x plus 2, close bracket, plus 1. So I'm looking for the amplitude, the median, the midline, the period, the max, the min, the y-intercept, and the x-intercept. From the equation, Brandon knows that we've got to memorize what A, B, and D are doing. The C value is less important. It's called a phase shift. All you need to know in this course is that if there's a C value, there's been some phase shift. That's the extent of what you need. But if I'm looking at this one, and I say, okay, I'm going to find first the amplitude, the max, the min, and the median. Because those are, median. Because those are probably the easiest to find. Using the theory from the previous page, the amplitude is the A value. Since that where the arrow is pointing is the A value, the amplitude is 5 units. Okay? That's it. Also, too, I'm going to look for the median. I'm skipping to the end one. The D value where the new arrow, okay, the double arrow, the thicker arrow is formed, that one there is the median. The median value is +1 or 1. Okay? It's that simple. You have to look for those values. Now for the maximum, if I asked May what the question or what the formula would be, the maximum is the D value plus the A value. The D value is +1 plus the A value, which is +5. The maximum is going to be 6. For the minimum, it's going to be the D value minus the A value. It's 1 minus 5, which is -4. Now, keeping in mind what we know about these things, the median is 5 away from the max or 5 away from the min, which is the amplitude, which is what we're talking about anyway. When we were doing it before, the median is exactly halfway between the max and the min. Exactly halfway between 6 and -4 is +1. So we can do it that way. So I've found the amplitude, the median, the maximum, and the minimum so far. Midline. Midline is actually talking about the definition or the equation of a line. Shh. So the equation of this line is a horizontal line. So the midline, by definition, is y equals 1. The equation of the midline is y equals 1. The y equals is important because without the y equals, it's not a horizontal line. It's not a midline. It's just a number. Okay? So you have to have the y equals. Honestly, your textbook doesn't always get it right. Sometimes it forgets the y equals. But the y equals needs to be there. So I've got the midline. Continuing on with this, I'm going to find the period. Now the period from the theory is 2 pi divided by b. Okay. B is this one here where the triple arrow is. B is 1/2. So it's going to be 2 pi divided by 1/2. And I go into my calculator. Now you have to be careful when you do this. If I go out to the main screen, it's going to be 2, pi is right up here by the little hat, 2 pi divided by 1/2, bracket 1 divided by 2. 2 pi divided by 1/2. You'd have to remember the brackets. You're dividing by all of it. Hit enter. Your period is going to be 12.566. Okay? The period is 12. Now, depends on the context as to whether that's useful or whether that fits or something. But that's what I'm going to do. The period is approximately 12.566. Okay? For the y-intercept, and the bell's going to go right away. For the y-intercept, you let x be 0. So you're going to have y equals 5 times the sine of 1/2 times 0 plus 2, and then close the bracket plus the number 1. And you go and type that into your calculator, and that's going to be your y equals 5 sine 1/2 times 0 plus, what was that number value I forgot? Plus 5? Plus 2? And then plus 1. And if it's in radian mode, it'll give you the y-intercept is 5.54. It may be a number or nicely, it may not. So y equals 5.54 approximately. There's no homework today. We'll take this up again tomorrow. I'll start here with the x-intercepts. Have a great day.